welcome to Algebra 2. We've got section 3.3 today, completing the square. All right, for our introduction, we've got a little calculator practice. And again, I encourage you to pause the video right now, plot these two functions in the y equals menu of your calculator, and come up with an answer on your own here for the little question prompt at the end. What stays the same? What do those have in common? What is different? Okay, so go ahead and plot those now. I'll check back with you in a couple seconds. Okay, hopefully we've come up with some answers for the questions at the bottom, and we got those two graphs plotted appropriately. I'm going to pull up the calculator here, and I've already typed those functions in. And if we look at those on a standard window, you see we don't really get a good look. They kind of just look scribbly there for having the two functions typed in. So what I'm going to do is we can adjust the window. It looks like going from 0 to 10 would be a more beneficial x-axis range, and we want our y-axis to show a little bit more. We don't see where the vertices are, each vertexes of those two graphs. So under window, for x-min, I'm just going to type in -2. That'll show me the y-axis, and it'll also not show me all that empty space off on the left. So it's going to start at -2, working all the way to the right to +10. For y minimum, let's go -40. And then y max, we can leave that as a +10. But we can adjust the window to better fit the graph. Let's take a look now. And now you can see our x-axis is taking up the screen where the graph is, and then our y-axis has been scaled so small that we can see the vertex of each function. So as far as what remains the same, what changes, well, here's what I see. I see that the first function, the thin line, has a vertex that's much lower, and you can see it looks like it is much steeper. So, the 2 out in front of that x squared telling us it's twice as tall, definitely living up to its reputation there. So that is one difference that I notice. The y-intercepts, where each graph crosses the y-axis, they're going to reflect that change as well. So what was the y-axis for the second function, the darker graph, that's going to be, or the other graph will be twice as high. Again, living up to that 2x squared. Then what stays the same? Well, those graphs both have zeros at the same exact spot. So they have the same solutions, even though they are two totally different graphs. All right, so what remains the same? The axis of symmetry stayed the same, and the x-intercepts stayed the same. What was different? The y-intercepts were different, and the vertex was different for each of those two graphs. But again, we've been spending a lot of time on solving quadratic equations, so the fact that the x-intercepts remains the same, that's going to be a big component to our work today. Also, a nice little opportunity to look at the calculator, customizing the window to show us what we want to see. That's something that a lot of students go through their math career, sadly, without experiencing. All right, so we're trying to complete the square today. That means our work is going to hinge around having a perfect square. It's a number that can be expressed as a factor times itself. So, for example, in numbers, you can start off from what we know. 64 is a perfect square number since it can be written as a factor times itself, 8 times 8, or 8 squared. A perfect square trinomial is a trinomial, and that just means it has a squared term, an x term, and a number, right? 3 pieces to that expression. It can be written as a square of a binomial by factoring. So if we were to factor x squared plus 6x plus 9, the result of our factoring would be x plus 3 times x plus 3. So we could in turn write that as x plus 3 squared. Now if we're looking to solve, there's only one x that we have to get rid of everything else around it in order to solve for x. It makes our solving much simpler. Likewise, the second example here, if we factored it, we get x minus 5 times x minus 5. That's a perfect square trinomial because we could call that x minus 5. Sorry, it's harder to get to my eraser here. X minus 5 squared. All right, so what we've come up with is a process called completing the square to turn any equation into a situation where we have a perfect square trinomial. So just some small adjustments that we need to make. All right, so to explain this process of completing the square, I came across this excellent visual explanation. A colleague of mine showed this to me. So if we have an equation like x squared plus 10x equals 29, well, you would think that, oh, we have to get this set equal to 0 and try to factor it and work from there. But this completing the square process will allow us to solve this without having to go through all that work. So if we think of x squared, when you think of something squared, hopefully you think of like the area of a square. So here this orange area is x times x squared. Then we're adding to that 10x, which we could think of as a measurement of 10 times that same height of x, right? The area of a rectangle, 10 times x. And we want that to equal some amount of area that is 29 units. Well, all we want to do in order to be able to solve this using our square root method is turn this x squared and 10x, turn that into something squared, make it a perfect square. So to visualize this, if we want to set up a square that we can complete, this is kind of an interesting way of thinking about this. Let's take a look at that rectangle that's 10x. If I divide that in half, then I have two rectangles that are 5x. And then adding them to that orange area means we're just going to combine them together. So I'll move those two rectangles like so, and you can see it almost makes a square. There's just this little corner that we need to add in. And so if we add that area in, we can find out that that would be a measurement of 5 times 5. So if we add that same area to both sides of the equation, then we have the area of this square equaling that area of 29 plus the 25 that we had to add to keep that balanced. So now our equation is saying we've got a square that's x plus 5 times x plus 5. X plus 5 squared equals that other area plus 25. And we can combine like terms, and now we're free to square root both sides and solve. So very, very neat way of thinking of completing the square, and hopefully this helps find some patterns and remember the process. I really like this little visual proof. All right, so we're going to hang on to that idea for completing the square. Our first example is just to solve using square roots. Okay, so using square roots. Here's this completing the square and using square roots are the only cases where we do not want our function set equal to 0. If we factor r squared minus 10r plus 25, we get r minus 5 times r minus 5, and that's equal to 1. That means r minus 5 squared is equal to 1. And now notice that since we have something squared, we can square root both sides to get to the variable we're looking for. So r minus 5 equals plus or minus square root of 1. We did take the square root as a step of problem solving, so we need to include that plus or minus. So r minus 5 could equal positive 1, or r minus 5 could equal negative 1. If we add 5 to both sides, we get r equals 6. Add 5 to both sides, we get r equals 4. And those are our two solutions. All right, example 8. If we were to factor this, 169 is actually 13 squared. That's another little life hack thing. If you know your perfect squares, you're going to be a much stronger math student. It makes the math go much, much more quickly. So x minus 13 times x minus 13 is what we're looking for. That equals negative 13. That means, since we had x minus 13 times itself, x minus 13 squared is negative 13. And we're good to square root both sides now. Square root cancels out the square. X minus 13 equals plus or minus I root 13. Okay, right, we had a negative underneath the square root. That's okay now, because we've got complex numbers in our number system. If I add 13 to both sides, I get 13 plus or minus I root 13. Okay, and those are the two solutions. This is just a situation where our graph did not reach a height of negative 13, so imaginary solutions act as placeholders there. Example 2, find the value of c that makes the expression a perfect square trinomial. Then write the expression as the square of a binomial. So this is pattern hunting to the nth degree here. And let's just think of our little square situation that we had here from our little introduction animation thing. So we have this x squared, and then we have a 22. I'm just going to kind of ignore the fact that it's negative for now. 22x. Remember, we divided that in half and then combined that with the other square that was there. So we have to divide that 22 into two 11s, and then that will help us determine that c. So what would end up happening here as well, when we combine those rectangles together, what we get are 11s, and then this little square in the corner is going to be 11 squared. So we've got x squared minus 22x plus 11 squared. We divide this number by 2, right? That's this cutting in half process, and then we square it to make that little square in the corner. So x squared minus 22x plus 121, and then we could choose to factor it, but hopefully we're starting to see some patterns when we go about factoring this. We get x minus 11 times x minus 11, or x minus 11 squared. You'll keep seeing this number that you squared to for your c value. You'll keep seeing that show up with the same sign on your b term inside that factor. That is a pattern that holds true. So I guess we should have said c equals 11 earlier up here. Let's see what happens here in this next one. We got x squared plus 9x plus c. Okay, well the c value is going to equal 9. We divided it by 2 and then squared it. That's just streamlining the pattern of what we talked through in number 14. That equals 81 over 4. Square the top, square the bottom. Okay, so we found our c value. Now, let's see if we can't go right to our solution. We have an x in our factor, and then this is a positive 9x, so we want plus that 9 halves squared. Right, the 9 halves was the number that we squared to find c, just like we did with the 11 over here. That is our binomial squared. And if we were ever curious, we could FOIL that back out and see if we get back to x squared plus 9x plus the c value we found. All right, example 3. I love the fact that the textbook uses that same proof concept. So here, find the value of c. Well, we just need to know what's this length times what's this length. c equals 8 times 8, which is 64. So the expression represented by this diagram is x squared plus 16x plus c. And if we include our c value, we could call that x squared plus 16x plus 64. Or, if we wanted to express it as a binomial squared, another expression, we could call it x plus 8 squared. So just kind of tying all those ideas together. All right, now do we get to the important stuff. Not that the other examples weren't important. Those are the building blocks. To solve an equation by completing the square, this is again, really one of the rare cases where we do not want we do not necessarily want this equation set equal to 0. We want all of our s terms, in this case, all of our variable terms on one side of the equation, and I'm going to add the 6 over to the other side. And this is just like if you go back to that visual example, just like having the squares equal some starting area. That's where we're at right now. Okay, now we need to complete this square in order to set up s something squared, a binomial squared on the left. So here's where we run through our pattern. What do? We divide that b term by 2 and get a positive 1, and then we square it. So we have to add that little yellow square of plus 1 in this case. And whatever we do to one side of the equation, we have to do to the other side as well. So now I've got s plus 1 squared equals 7. And now to finish solving, we're at the point where we can square root both sides. S plus 1 equals plus or minus root 7. And then s equals negative 1 plus or minus root 7 when we subtract that remaining 1 from both sides. Okay, let's look at 34. Okay, here we don't even have our squared term and our regular variable term. We do have our constant moved over to the right-hand side, which is nice. So we got 4w squared minus 12w, that's just distributing this 4w, and that equals 24. And I don't like this 4 out front, and that makes the work much more difficult to handle. What we're able to do is divide both sides by 4. And here's where our introduction comes into play. Even though this is 4 times as tall, it's going to have the same solutions as if it were scaled down. So we divide away that 4 times as tall, get w squared minus 3w, and then we're going to have to complete the square equaling 6. Now it's important that we do that to both sides of the equation, right? We do have to keep that equation balanced. All right, so what completes our square? Well, that 3w, if I divide that by 2, I get negative 3 halves, and then I square it. Square the top, square the bottom. Whatever I add to one side, I added 9/4. I'd better add that to the other side as well. Okay, so now we've got w minus 3 halves squared. I really like writing it out with these arrows because I can see that negative 3 halves. I know that's going to complete my factor at the end. That's kind of a nice little pro tip there. And then 6, well, that's 24 over 4. 24 plus 9 is 33/4. If I set that up to add with the common denominator. And now we're ready to square root both sides. We've got our term squared, or our expression squared, so we can square root it to undo. W minus 3 halves equals plus or minus square root of the top, that doesn't simplify, over square root of the bottom. Oh, nice, we've got common denominators. All we have left to do is add that 3 halves over to the other side. And we get W equals 3 plus or minus root 33. And that's all over our common denominator of 2. And answers that look like this are not uncommon when dealing with quadratics. So don't be alarmed if you have something that looks a little bit complicated like these two did. Totally fine. All right, our 5th example, determine whether you would use factoring, square roots, or completing the square to solve the equation, then solve it. Explain your method, or your reasoning in choosing the method that you did. Well, for number 44, you can see I've got something squared equals 9. Well, this is set up beautifully. I can just jump right into square rooting both sides. X minus 7 equals plus or minus 3. So x would equal, let's add 7 to both sides. Negative 3 plus 7, or positive 3 plus 7. So it was pretty evident that the square root method was the one that we chose because we were set up with a perfect square. Our equation took the form of something squared equaling a number. If we see that right away, we should be expecting using square roots to be an appropriate method. All right, number 48, well, we don't have that nice form to use square roots, so that one's out. Maybe we should try factoring. 3 times 1 is 3. What multiplies to be 3 and adds up to 12? Yeah, good luck. All right, well, let's try completing the square. So here we'll get it set up, 3x squared plus 12x, and something where we complete the square, we want to subtract that 1 over to the other side. Okay, again, I've got something in front of this x squared. I don't really like working with that, so I'll divide both sides by 3. Yeah, I know that sets up a fraction on the right, but it makes the completing the square much more manageable. So now I've got x squared plus 4x plus something equals negative 1/3. All right, let's complete the square. That b term, we'll divide it by 2 and square it. So plus 4. Whatever gets added to one side must get added to the other, and I'm going to call that 12 over 3 instead of 4, so I have a common denominator. And so now we have our perfect square, which we can call x plus 2 squared, and that equals 11/3. We're good to square root both sides of that equation. So we get x plus 2 equals plus or minus root 11 over root 3. Well, we don't like that square root in the denominator. So what we might do before we move on is just think, okay, root 11 over root 3. Let's multiply the top and bottom by root 3. It's just like multiplying by 1, so it doesn't change the value of it. I would get root 33 over a regular 3. Okay, so x plus 2 equals plus or minus root 33 over 3. And then we would subtract 2 from both sides. That's like subtracting 6 over 3 with our common denominator. So x equals negative 6 plus or minus root 33 all over our common denominator of 3. Okay, and it is customary to put any real numbers, I should say whole numbers out front before your radical, just so you don't accidentally think that that 6 belongs underneath the radical with 33, just to keep things clean. All right, example 6. Write the quadratic function in vertex form, identify the vertex. So we want to get to this y equals, or f of x, g of x, h of x, our function equal to a times x minus h squared plus k. So you can see where that perfect square, or that binomial squared, comes into play, and completing the square definitely does help us with that. All right, so I've got g of x. I'm going to complete the square with these x terms. I see an x squared and a regular x term together. I want those on the same side of the equation. So I'm going to add the 1 to join the g of x. Add 1 to both sides. And now we get to the point where we have this square that needs to be, or this trinomial that needs to become a perfect square trinomial. So we got our b term of negative 4. We divide that by 2 and square it. So we add 4. Whatever we do to one side, we have to do to the other side as well. So now I've got g of x plus 5 equals, and now I'm ready to call this x minus 2 squared. Again, that negative 2 that was half of our b value is what goes into that factor. And the last step is to subtract the 5 back over. Now that the completing the square process is done, we can move that back over to the other side of the equation, and we get our function in vertex form. The vertex of that function is positive 2, negative 5. Just tying this new process in with what we've already learned in chapter 2. All right, let's try the same process in 58. Here we got h of x. We want to get that constant of 90 subtracted over to the other side. So we subtract that from both sides of the equation. And we got x squared plus 20x, and we're ready to complete that square. If I divide that by 2, I get positive 10. And square it, I'm adding 100. And whatever I do to one side, I better do that to the other side as well. So h of x plus 10 equals x plus 10 squared. And the last step, put it into our vertex form, subtract 10 from both sides, minus 10. And we'll just grab our vertex out of that. It ends up being negative 10, negative 10. All right, example 7, a skateboard shop sells about 50 skateboards per week when they're priced at $70 each. For each $1 decrease in price, one additional skateboard per week is sold. Shop's revenue can then be modeled by this function in intercept form. All right, and let's just kind of take a look at what that means. So here, 70 minus x. Well, that means I have an x-intercept of 70. And here I have an x-intercept of negative 50. All right, and trying to find a maximum point there. So we should see a parabola that's opening downward. And if we tried to FOIL this out, certainly we would see a negative x squared when we do negative x times positive x. So that makes sense for us. Use intercept form, which was given, to find the maximum weekly revenue. All right, so this really doesn't have anything to do with completing the square today, but it's a nice additional look at how to navigate quadratic functions and parabolas. So let's see, if our two intercepts are negative 50 and 70, then we know that our axis of symmetry, which will give us the x value of our vertex, and the vertex, of course, will be the maximum, will be the location of the maximum. So x equals, I've got negative 50 plus 70 over 2. That tells us x equals 10. So when x equals positive 10, that's where our vertex is going to be located. To find the actual maximum, that's going to be y equals 70 minus 10 times 50 plus 10. 60 times 60, which is 3,600. Okay, so maximum revenue, $3,600 when they price their skateboards $10 below 70. And here's a look at your assignment for section 3.3.